So, looking at the first example, you see it's the sine of the arc cosine of 4/5. Now, the result of any kind of inverse trig function is an angle. All right. So, while this is something you could type into your calculator and get an answer, and that answer would be nice, you gotta remember it's not pre-calc, it's not an algebra class. So the question you're going to be asked is not going to be this. It's going to be something like find the derivative of this. Right? So knowing how to work with it algebraically, or at least analytically, makes more sense. So we're looking at the sine of this theta. Now this theta has a ratio of 4/5, so that ratio makes up the components of an associated right triangle. So again, that's a ratio. So if I were to draw the corresponding triangle related to that, the cosine ratio is adjacent over hypotenuse, so 4/5. What I need is the sine of theta. That theta being right here. All right, the sine of theta is opposite over hypotenuse. So if that's the case, in that triangle, I need the opposite side, which would be what? 3. All right, so the sine of theta, which is really the sine of the arc cosine of 4/5, because the arc cosine of 4/5 is the same as the theta in this triangle. That sine ratio is 3/5, and so therefore the sine of the arc cosine of 4/5 would actually be 3/5. All right, so that's the pre-calc variation of this. Now, and B also is pre-calc, but then eventually we're going to have to get to the calculus of it. So let's see what it looks like in algebraic form. So similar question, actually almost exactly the same, except we're going to have a variable ratio rather than a numerical one. So we still have a theta. We're still going to have a corresponding triangle related to that theta. We still have a ratio embedded in that theta. This time the ratio is just written as x, but it's an implied x over 1. You could tuck a little over 1 in there. All right. So again, the cosine ratio, just following the same progression, the cosine ratio, adjacent over hypotenuse. All right, so my adjacent side is x. My hypotenuse would be 1. What would my missing side be? Radical 1 minus x squared. All right. So if I'm looking for the sine of theta, and again, theta is related to this triangle, I'm looking for the opposite side over the hypotenuse. Opposite is that radical expression, hypotenuse is 1. So the sine of the arc cosine of x is equal to the square root of 1 minus x squared. All right, so a little connection there between a radical function and a trig function. So what that's telling me is that I can represent a radical functions of certain varieties as trigonometric functions. So why would you ever want to do that? Sometimes it's easier to take the derivative of the trigonometric function than it is to take the derivative of the radical function. Now in this case, I think it's 6 to 1/2 dozen the other. I don't think it makes a difference. Right? In either case, there's chain rule involved. If you happen to know what the derivative of arc cosine of x is, the rule for that, which you wouldn't know yet, but you'll know by the end of this class. If you know that, and you'll have to have it committed to memory anyway, then these are equally difficult questions. But if you have no idea what the derivative of arc cosine of x is, then you would have no choice. You wouldn't be able to take the derivative of this expression in this form. You'd have to convert it over. Convert it over into this form by creating a corresponding triangle. We now know that these are equivalent expressions. I can find the derivative of this just by knowing the derivative of this. All right. And that we can do using chain rule. All right. So it's starting to slowly take shape. Very exciting. I mean, I'm pumped. I could tell by the expression on all of your faces that you are too. So again, we have a ratio. Related to some angle theta. Corresponding triangle. All right. So the tangent ratio. So they're telling me it's 3x, so I'm writing 3x over 1. Tangent ratio is opposite over adjacent. So the opposite side, 3x. Adjacent side, 1. What's my missing side? One plus 9x squared. All right. So then I'm looking for the secant ratio. I'll just make a little note of it on the side. Secant of theta, reciprocal of cosine, would be hypotenuse over adjacent. So I want my hypotenuse, the 1 plus 9x squared, or 9x squared plus 1 under the radical, over the adjacent side. The adjacent side is equal to 1. So nasty becomes not so nasty. Okay. This one in D, I would say no. You know, if you knew the derivative rule for arc cosine, not too bad. No difficulty difference between left and right. But here, I'd say there's a significant difference, because if I'm applying the chain rule, I first have to take the derivative of secant, which is secant times tangent of this inner function multiplied by the derivative of the inner function, which has its own inner function. So that's going to be pretty messy. It actually cleans up kind of nicely, but it's not going to be as nice as working with this, which is much simpler. All right. Maybe it wasn't that simple when we were looking at chain rule for the first time, but now that we have some experience with chain rule, it's mere child's play. All right, so let's talk derivatives. Well, in order to be able to do some of these things, it would help us if we knew some basic derivative rules for things like sine or arcsine. Well, the three major trig functions. All right, not SOHCAHTOA and TOA, not sine, cosine, and tangent, but sine, secant, and tangent. All right, those are the three most important ones because everything else is based off of those three. They just couldn't make a fun acronym out of those three. Anyway, the arc sine of u. That's what I want to find the derivative of. I'm going to write it as y equals the arc sine of u. All right. Now, I'm going to make a slight modification to this because in its current form we have an issue. Now one way to handle it would be to convert it over to algebraic form like we did above, or like we learned how to do above, take the derivative and then see where that gets us. Maybe we can write it in terms of the trig function after the fact. That's possible. I'll actually show you both ways. One way is kind of a cool application of implicit differentiation. The other way is related to the algebra. So we don't know the derivative of arc sine, that's why we're here, but we do know the derivative of the sine function. So what we can do is take the sine of both sides of the equation. So sine of y, is along the lines of what we did yesterday, which is why we did what we did yesterday. All right, so we have sine y equals u. All right, because the sine of the arc sine would cancel, making our equation, I'm just reversing the order, u equals the sine of y. All right, so it's an explicit equation, but solve for u in terms of y rather than y in terms of u, but we can still work with it. So I'm going to take the derivative of u with respect to y. All right, so my independent variable is y, so we don't have to actually use implicit techniques. We just have to kind of consider that it doesn't always have to be y in terms of x. All right, so what is the derivative of the sine of y? Cosine y. All right, so then, all right, well, you got to think this through. What is it that we're looking for? This arcsine of u is my y equation, or y expression anyway. So dy, d of this y, dx. So essentially I'm looking for dy dx. I have du dy, all right, not quite what I'm looking for. So let me make a little modification here. I'm going to flip the du dy, and I think when we were talking about logs, natural log, when we were coming up with that rule, we were talking about the idea that that's a legal move. If you flip one side of the proportion, that's okay as long as you flip the other side too. All right. So we're looking at dy du equals 1 over cosine y. All right, but again, I want dy dx. All right, so what can I do to dy du in order to make it a dy dx? Multiply by du dx, exactly. All right, so I'll do that on both sides, because that's just how math works. And so left-hand side becomes dy dx. Right-hand side becomes cosine 1 over cosine y du dx. dy dx, sorry. Oh, no, du dx. I said it right the first time. Then I started writing it the wrong way. Crikey. All right, so this is a way of representing our derivative, but it's not the best way, because if I have a dy dx, ideally, I'd like to have it in terms of x. I'll settle for having it in terms of y if I can't make a substitution that allows it to be in terms of x. All right, so how do we make the substitution? We have a ratio here. The arcsine is of u. That ratio is the opposite over hypotenuse ratio. So u over 1 with an opposite side of u, hypotenuse of 1. All right. What would my adjacent side be? U squared minus 1?
1 minus u squared.
Okay, so then I'm looking for the cosine of y. All right, well, okay, so what's y? Well, that's the challenge. If I'm defining this whole shebang as y, because I'm saying I'm looking for the derivative of y with respect to x, but we also know intuitively, or just based on the fact that I flat out told you, the arc functions, they always result in an angle theta. What that's telling us is that y and theta are thought of as the same thing in this case. All right, so y would be equal to theta. All right, so if I'm looking for the cosine of y, it's really just a justification. I'm making the assumption that this y, because it's equivalent to theta, is referring to this triangle. So when I'm looking for cosine of y, I'm looking for adjacent over hypotenuse in this triangle. Adjacent side is the root, hypotenuse is 1, so the cosine ratio would just be the square root of 1 minus u squared. All right, so I now have an expression, all right, well, not totally in terms of x, it has u's and x's in it rather than y's, u's, and x's, so we improved the situation, and that's all we were really looking to do. Come up with the best possible expression to represent the derivative, right? And this actually ends up being the chain rule expression to represent the derivative of the arcsine function, right? So if I know what the u is, then I can figure out what the derivative is just by plugging it into this model, all right? So pretty funky stuff. We'll do it again with the arctangent in a second, but before we all freak out and start thinking that, man, we're gonna have to do this every single time. One, you won't, because this now becomes a rule that you can rely upon. Just like when we discovered that the derivative of sine was cosine, we learned along the way that, okay, as long as you know the derivative of sine is cosine, you don't have to show all the limit steps that got you from sine to cosine. Same idea here, but it is something that you have to memorize, all right? Add to that the fact, or maybe the silver lining to that black cloud would be the idea that there is a relationship between the derivative of arcsine and arccosine, and that they are negations of one another, all right? So if you know the derivative of arcsine, all you have to do is negate it, and you have the derivative of arccosine. All right, when you gain a little bit of experience with this, what you'll start to realize is that you never really will ever need the cofunctions when it comes to this concept, unless you're expressly asked to find a derivative or antiderivative related to them. Because just kind of moving forward into the second semester, you're going to ask to find an antiderivative, so working backwards, find the function that has a derivative equal to a particular expression. If I gave it to you in this form, you could still come up with an arcsine as a result just by applying a negative to it. Okay, so, but it's good practice at this point. The good thing about this kind of trig function, inverse trig function, is that if you wanted a second look at the derivative of arcsine on your own, you just do arccosine, because it's almost exactly the same in terms of process, and you already know what the answer is going to be, right? So that's going to be one of your practice problems, right? But we'll move on to arctangent now, and like I said, these are all going to support each other. So if you didn't fully get it the first time around, the second time will make things a little easier. The third time around, even easier. All right. So arctangent, you can kind of streamline the process a little bit when you're doing it on your own. I'm going to pretend that that's the very first problem we're doing, so I'm going to pretend that can happen just so we get another look at it. All right, so we're looking for the derivative of this y per change in x. All right, so we have this as my y equals the arctangent of x, arctangent of u. Again, if we knew what the derivative of arctangent of u was, we wouldn't do any of this. Because at this point we would just say, here's my answer. All right, but we don't have that benefit. We need to discover it. All right, so what we do is we take the tangent of both sides, or find the tangent of both sides, because we do know what the derivative of tangent is. All right, so I'm going to take the tangent of both sides. So we're looking at tangent of y on the left-hand side, and then the tangent of the arctangent of u, which would be what? U. All right, so we're looking at u equals tangent of y. You can skip that step, that intermediate step. Yeah, I mean, when people get the hang of this, they skip both of these steps. They go from right here to here, figuring that, mentally, if y is arctangent of u, that u would have to be the tangent of y. Go right to it. Then take the derivative, du dx, du dy, and the derivative of tangent y would be secant squared y, and that would be over 1. All right, it's over 1 because we're going to do that reciprocal magic. and get dy du equals, well, if I take the reciprocal of secant squared, I get 1 over secant squared, sure, but that's the same as saying cosine squared. All right, so then I need dy dx, so that's where we multiply by du dx to both sides. Let me just get this in here. So I'm multiplying by du dx. Left-hand side cleans up to a nice dy dx. The right-hand side is cosine squared y times du dx. And again, just like the last one, we want it completely in terms of x. We'll settle for u's. We generally don't want to have y's, u's, and x's. It's too much. It's not really advancing the thought. All right. But again, if it's not possible to get rid of it, then you're stuck with it. You just live with it. All right, and that would be your final answer. If it is possible, it's like exactly the same time. So let me draw a little triangle here. I mean, you could put y in as the angle, but it just feels wrong when you do it. I mean, if you actually draw a little y in here and the label of the triangle, when you look at it, you're gonna be like, that just feels wrong. Little thetas are nice. Thetas belong in triangles. So y and theta are the same thing because again, arctangent, arc anything always results in some angle. All right. The ratio is u for tangent opposite over adjacent. So u over 1. Hypotenuse would be what? 1 plus u squared plus 1. Either way, it's going to work. All right. So cosine of y, which is the same as cosine of theta, adjacent over hypotenuse, so 1 over the radical but squared, would be 1 over 1 plus u squared times du dx. Okay. Maybe for this one, I'll show the alternate approach, just so you get a handle on it. So, had you decided to do the triangle business first, you could come up with a new relationship, arctangent. Oh, actually, no, because I don't even know that you could. Hold on, let me just think about this for a second. Because the arctangent. No, it would still be of the angle. You would need like the tangent of something. Yeah, the other method is still going to rely on some of this stuff. I don't know if it works, but yeah, come back to it. Secant.
Which can?
If we say y equals arctan u, then couldn't in the last step we just plug in arctan u?
In the last, oh, here?
Yeah.
Yeah, it would be cosine squared of arctan of u. But that can be simplified.
Okay.
And when you simplify it, it's going to become this.
Okay. It's just easier that way.
All right, so again, this is my y. So, like in the previous one, like I said, we're writing as y equals arc secant of u. To just take the secant of both sides and come up with, instead of y equals arc secant of u equals the secant of y. So differentiate du dy would be equal to, and what's the derivative of secant? Secant x tangent x, in this case secant y tangent y. All right. Now, up to you if you want to convert over to sines and cosines. We do have to take the reciprocal of each. So in some cases it'll get nicer, in other cases not so much. So when we flip it, or in one case it'll get nicer. So dy du, the reciprocal of the secant would become a cosine. All right, because it's going to become 1 over secant, which in turn becomes cosine. But then you have 1 over the tangent, which is going to become cotangent. The long and short of it really is the idea that it doesn't make a difference. Because we're going to have to draw the triangle, we're going to have to come up with ratios, and we're going to have to plug those ratios in anyway. So whether you call it secant, 1 over secant tangent, cosine, cotangent, cosine over tangent, or in this case it would be cosine squared over sine. You could do it that way. If you were to convert it over completely, it's not going to make a difference one bit. So you can go in any direction you want. All right, so dy dx, if we multiply both sides by du dx, would become cosine y, if I'm working with this form, cotangent y times du dx. Let me just draw the triangle here this time. All right, so we have some angle theta. That's the same as y. The secant ratio, u over 1, is hypotenuse over adjacent. So my missing side would be what? Radical u squared minus 1. It's going to be the hypotenuse squared minus 1 of the legs. Cosine is adjacent over hypotenuse, so 1 over u. The cotangent is adjacent over opposite, so 1 over square root of u squared minus 1, which we can make into a single fraction. Oh, I forgot my du dx. So 1 over u times the root of u squared minus 1. Get rid of the extra schmutz here. Times du dx. Now, in trig, we define it so that the hypotenuse is always in any kind of unit circle triangle, and these are all unit circle based values, or at least circular trigonometric values, in which case the hypotenuse always has to be positive, right? And since u represents the measure of the hypotenuse, that needs to be a positive quantity. So I'm going to slap a little absolute value bracket around that. All right, so otherwise it violates the laws of trigonometry. Right, so going back to how a unit circle is created, Algebra 2 or pre-calc, wherever you learned it. All right. So anyway, the cofunctions are just negations of these. So take your arc secant and negate it, and you have your arc cosecant, and the same idea for the arctangent. So those remaining problems are yours to do with as you wish. You could practice with those if you want. Well, actually, let's write it as, it's going to be more convenient this way. Bless you. U prime over the square root of 1 minus u squared. Okay, instead of writing it as 1 over the square root of 1 minus u squared times u dx, we'll use u prime instead of u dx and just put it as the top of the fraction, because when you simplify, that's probably what you're going to do anyway. You're going to take it and multiply, take the two parts, multiply them together, and odds are it's going to look like something like that anyway. All right, arc cosine, same thing but negative. Arctangent, u prime over 1 plus u squared. Arc cotangent, negation of that. Arc secant. U prime over the absolute value of u multiplied by the square root of u squared minus 1, and then again the negation of that for the arc, the negative cofunction, or the cofunction itself, arc cosecant. All right, so the derivation is definitely fun, but the application of these, like actually using the rules, not bad at all, because if you actually know them, then, I mean, just look at this. We have our u here. And just follow a model. U prime, all right, well, the derivative of that is 2. On the bottom, the root of 1 minus the u, whatever the u is, in this case 2x squared. So the root of that 2x squared, 1 minus that, would be 4x squared. All right, so just knowing the rule is enough to get you the solution. All right, same idea for the arctangent. All right, so 3 over 1 plus 9x squared. Arc secant, it's a little kookier, but especially because it's a little beefier in terms of the model, but also it's a e to the 2x. So on the top, I need the derivative of e to the 2x, which would be what? 2e to the 2x. On the bottom, I need the absolute value of u. Now, u is e to the 2x. Can that ever be a negative quantity? No, so I don't need the absolutes. All right. On the inside, I'm squaring my u, so I'm squaring e to the 2x. So e to the 2x squared is what? E to the 4x. So this one would clean up a little bit, solely based on the fact that that absolute value goes away, and that is 2 over the root of e to the 4x minus 1. Now, the last one, this goes back right to the I think the second or third example. You have a choice. It's pretty much the same either way. It's converted over using a triangle into an algebraic form and then take the derivative, or take the derivative using the chain rule and then clean it up. Either way, your answer should be an algebraic answer. All right. So sometimes it works out where you don't have to draw a triangle in order to come up with your final solution, but in most cases you will have to do that. So I'm going to do it in the way that will work in all cases. All right, so we have a ratio. I'll draw the triangle associated with that ratio. opposite over hypotenuse, missing side. All right, what would my missing side be?
Radical 1 minus 9x squared.
Minus 9x squared. Thank you. And then from that, I need the cosine. Cosine of the theta would be equal to adjacent over hypotenuse over a 1. So what that's telling me, all of that stuff, is that the cosine of the arcsine of 3x is the same as the square root of 1 minus 9x squared. And then using ordinary chain rule, we could find the derivative of this. Right? So, you know, it's 1 minus 9x squared to the 1/2 power, so 1/2 1 minus 9x squared to the negative 1/2 times the derivative on the inside, which would be negative 18x. All right, and if you were to clean that up, it'd become negative 9x over the square root of 1 minus 9x squared. If you apply the chain rule using your inverse trig functions, it still works out. So it's kind of cool. You'd be looking at, well, it's cosine of an inner function, so it would become negative sine of that inner function, negative sine of the arcsine of 3x. Multiplied by the derivative of the arcsine of 3x, which by rule now, so that's the important piece there, you need to know the rule, would be 3 over the square root of 1 minus 9x squared. So the negative sine of the arcsine of 3x would become what? Negative 3x. Multiply these two things together and you get that expression. So either way it's going to work out. The issue is the only reason why there was a cancellation here is because the outer function had a derivative that was the inverse of the inner function. If I make this anything other than cosine, then all bets are off. You don't have that nice cancellation. You'd have to draw a triangle to evaluate this figure and come up with a solution along these lines. So more often than not, you're going to have to do it this way. So, you know, why not just get into that habit to begin with?
Why do we multiply by negative 18x?
Oh, because it's the derivative of the inner function by chain rule. All right, so you're going to want to practice, I mean, it's up to you, but the 3 problems that we skipped on the previous page, but definitely do this one also by hand. Don't do it on the calculator.